Okay, so our next speaker, Jermyn, will speak on elastic metric for surfaces and its use. And so, isn't this where you came in? Elastic metrics?
Yeah, that happened. Yes.
It happened to you.
Okay, hi everyone. Thank you, Daryl. Thank you, Martins, for the invitation to speak. This is work that's been done in collaboration with several other people listed here. So I guess Anuj Srivastava, most of you know of. Sebastian Kurtek, who's now at Ohio State. He was a student of Anuji's Hamid Lager at Murdoch in Australia. Kian Zi, who was a student at Florida State, I think now is working for Amazon, I believe. And Eric Klassen, who's in the maths department also at Florida State. Okay, so I'll start off with some background, some sort of justification. So what I'm interested in talking about here is analysis of surfaces. So essentially two-dimensional surfaces in a three-dimensional space, but we'll see later that the work can actually be generalized to many other cases. So when I say shape, I don't mean the classical Kendall definition of shape. I mean something simpler, just an unparameterized surface, for example, in R3, like this, a geometric object. And we're interested in doing statistical analyses of these things. So one way to do that, at least, is to try and define concepts such as mean and variation, as would be used in classical statistical analysis. But in order to do that, we need to define a distance between these objects. It's useful if that distance, as well as simply giving us a number for two different surfaces, actually also gives us, or is in fact, the length of a path deforming one of the surfaces into the other surface. This gives us a nice interpretation of the distance as an optimal deformation between one surface and another. That doesn't have to correspond to any particular physical model, but it gives a nice intuitive picture of what's going on. We might also want this distance to depend on a registration between two surfaces. So by registration, I mean a one-to-one correspondence between the points on one surface and the points on another surface. So that's the goal. How should we do that? Well, one way to do it, which is what I'll talk about, is to define a Riemannian metric on some space of parameterized surfaces. The audience may be a bit mixed. So parameterized surface is a map from, say, in this case, a sphere into a three-dimensional space. And the sphere is sort of deformed to produce this surface. So we have a whole space of these possible parameterized surfaces. Parameterized because we have a name, essentially, as some coordinates here, which give labels to points on the surface. And a Riemannian metric, for those who don't know, is simply a way of measuring the length of infinitesimal changes to an object. So in this case, this quantity g will give a size to a small deformation of the surface. And our job is to define this. So why would we do it this way? For the following reason. So we started off looking at unparameterized surfaces, but now suddenly I've introduced these parameterized surfaces, so why would I do that? Well, we use a Riemannian distance precisely because the Riemannian distance by definition is the minimizing length of a path between two shapes. So we have this idea of an optimal deformation. And we use parameterized surfaces because once we have two parameterized surfaces, we automatically encode two unparameterized surfaces and a registration between them. So that's illustrated here. So here we have two surfaces. Here we have a sphere which is mapping into R3 to give these two surfaces. And it gives a registration because each point here is mapped to a point on each of the surfaces. So a point here and a point here are registered. They correspond to one another if they come from the same point back in S2. So by using parameterized surfaces, although we apparently introduce a lot of redundancy in the description, we get a registration sort of for free in the description. So by defining this framework, what we end up with once we have a metric on parameterized surfaces is both a distance between unparameterized surfaces and an optimal deformation between the registered surfaces. If we then optimize over the reparameterizations of one of the surfaces, essentially we're optimizing over all possible registrations, and once we've done that, we end up with three things. We end up with a distance between the unparameterized surfaces, which is between the distance between the parameterized registered surfaces. but we also end up with a correspondence and this optimal deformation path, which are very useful for many purposes. So this framework is nice in the sense that it's all based on the definition of this single Riemannian metric on parameterized surfaces. Then the question arises, of course, which metric should we use to do this? Okay, so some things that we might like this metric, properties we might like this metric to have. It should perhaps in some sense depend on meaningful changes in the surface. We don't want it to be arbitrary. We wish to be able to interpret the changes that actually happen and give some physical meaning to them. We want the distance in the end to depend not on the individual parameterizations of the two surfaces, but only on their registration. And the point here is that if I reparameterize both surfaces in the same way, their registration won't change because the correspondence won't change. And we also may want the distance, or do want the distance, to be invariant to rotations and translations, because if it isn't, it means that we're essentially selecting some preferred position and rotation for shapes, which in general we have no reason to do. So these two desiderata here mean that we have to have certain property of the metric, and that is that the reparameterizations of the surfaces, if we make a simultaneous reparameterization of both surfaces, and we make a simultaneous rotation and translation of each surfaces, the distance should stay the same. So these criteria constrain the types of metrics that we're going to look at. We also want computations to be practically feasible, so it's quite possible to define very complicated metrics between surfaces that satisfy these criteria, but for which the computation is infeasible in the sense that it's impractically long. And a second criterion which is sort of related to this is a simplicity of the metric. The metric isn't the end of the story. We're going to build on top of this metric statistical models and so on and so forth, so the metric doesn't have to answer all our questions. So it's nice if it's a kind of simple structure that we can understand on which we can build further superstructure. And a point that will come back later is that the metric being local in the way that I'll talk later can help to ensure that these computations are feasible. So one possible choice to do this for surfaces is something called the elastic metric, which I'll describe next, and in particular a reduced form of it called the partial elastic metric. Okay, so to describe this, it's convenient to introduce some geometric quantities associated with surfaces. So remember, the surface is a sphere which is embedded into R3, and that means we can define an induced metric, Riemannian metric, on the sphere that's being embedded itself, simply by, remember that the Riemannian metric describes the length of small deformations, so if I look at a small deformation on the sphere and then move that small deformation into R3, I can calculate its length in R3, and by definition that will be the length of that small deformation on the original sphere. And that's actually given by the dot product between the derivative of this function and itself. And I want to rewrite that as a product of two parts. I think, two parts here, which I'll call R and G hat. So R is the square root of the determinant of the metric, and that plays an important geometric role because that measures local area. Okay, so that's if I use this induced metric to calculate the area of a small piece of the sphere, this is the quantity that I get. And that leaves behind G hat, which is G divided by R. And this quantity always has determinant 1. And that's invariant to conformal transformations that we heard about in the last talk. If I locally change the scale, this won't change. So that's one quantity that I want to look at, and the other geometric quantity is the unit normal. So this is an unnormalized normal vector divided by its magnitude. So this is a unit vector field all over the embedded sphere, and that's nicely complementary to this in the sense that it's given by a cross product between the derivatives of the embedding function with itself. Okay, so we have here three quantities, one which describes area, one which describes angles, and one which describes the orientation locally of the surface. So if we think of a small surface patch, which I'll call ds, that can change essentially in three different ways according to this description. Its area can change, so there's a small change in R. Its shape can change, so there's a small change in this unit determinant matrix here, which is actually effectively a 2x2 matrix, a small change in that, which more or less describes, you can think of it rather than a small parallelogram as a small ellipse, and its axes are changing length. And finally, we have the orientation of the patch actually in 3 space, and that's described by n hat, so we can make small changes in that. So we're going to make a metric built on these 3 natural geometric quantities. Okay, so how do we do that? We do it in the simplest possible way. So focus on the quantity inside the square brackets. So here you can see what is essentially delta r squared. Here you can see delta g hat squared. And here you can see delta n hat magnitude squared. They each have potential weighting parameters that sit in front of them. That's a prime, b, and c. And it turns out that in order to achieve the invariances that we want to achieve, we have to multiply each of them by these inverse quantities here. I won't go into more detail about that. So this thing in the square brackets is a measure of the change in a small surface patch. It's changing its area, changing its orientation, changing its shape, and all we're going to do is add up this quantity over the whole of the surface of the sphere S2, and of course in the continuum case that becomes just an integral of this quantity over the whole of the surface. It's useful to simplify this by defining a quantity zeta, which is now the square root of r, so it's the 4th root of the determinant of the metric. And if you substitute that into here, you end up with this expression, and you can see that not much has changed, except that now we have factors of zeta squared in front of these last 2 terms, and instead of having an r to minus 1 here, we just have zeta squared here. Okay, so this term is still describing changes in area. This term is describing changes in the shape of the patch, and this term is describing changes in its orientation. So this has a... Yep, go ahead. Sorry.
If you were concerned with shape, why would you put the orientation on the equal footing with all the other two?
What do you mean by equal footing?
The metric takes into account all of them at this.
It takes it... Well, you want to...
Why they are equal footing? Why? So, for example, if A and B are 0, the only change is orientation, then according to this, it's non-zero. But even though the shape hasn't changed.
But remember, no, this is a local orientation. So it's the orientation of each surface patch. So if I take some shape and I change the orientation of each surface patch,
Relative to each other.
yeah, the shape will change. Yeah. Each of these changes are local. So you think of a mesh, a triangular mesh, and you're changing the orientation and the shape and the size of each of the triangles. That's the way to visualize it. Okay, so this quantity, or this equivalently this one, is the elastic metric by definition. So I've already described how it measures intuitively meaningful changes in the surface. It can be shown that, as required, the diffeomorphism group, the reparameterizations, and translations and rotations act by isometries. They preserve this metric and its distance. Although this was written down for surfaces, it's actually very easy to generalize this to essentially all, well, any domain, essentially, manifold domain, not just a sphere, of any dimension. This is written down for surfaces in R3, so the codimension, the difference between the dimension of the shape and the dimension of the space it's embedded in, is just 1, but you can potentially have surfaces in higher dimensions, and then the codimension is higher. And it's very easy to adapt this term, which is a normal vector, to make it into a normal form, which is a way of describing essentially the normal properties of the surface in higher dimensions. And that's important because it allows you to talk about decorated surfaces. So you might have a surface which doesn't just have geometric properties, but has some other properties attached to it. It could be color, could be some kind of chemical property. Could be proteins, for example. I think 2 days ago we had a talk about shapes of cells, and the person who was speaking talked about how cells are often compared by using the proteins on the surface rather than the shape. And having higher codimension means you can use both those properties at the same time. You could also use this to treat evolving shapes. And it's also easy to adapt this to the case where the codomain is not simply R3, not only has more dimensions, but is actually a Riemannian manifold itself. Although when you do that, you lose some of the simplicity of this metric, which I'll just mention in a minute. So it's very adaptable, and for those who know the SRVF and the case of curves, in the case of curves, this quantity g hat is identically 1, so this term simply goes away, and you're left with these two pieces, and that's exactly the elastic metric on curves, and I'll talk about the equivalent of SRVF in a minute. So this metric is local, and by that I simply mean that this is a sum over surface patches of quantities defined on each surface patch. There's no derivatives of any of these quantities, so there's nothing that connects each surface patch to the neighbouring surface patch, and this means that finding geodesics in these metrics is particularly simple because you can look at essentially each surface patch independently, which Peter Meeker mentioned in his talk on Monday. So that's a very useful property in terms of computation and in terms of simplicity. So this metric has appeared before, so you'll notice this part, if we exclude this bit, this part is a metric on the space of Riemannian metrics on S2, which we heard a great deal about from Peter Meeker on Monday. And this is actually effectively the simplest of the metrics that he spoke about then. If we get rid of this term, we set C equal to 0. This is the metric that DeWitt talked about in a context of quantum gravity. And in a sense it's unique, not in a certain trivial sense it's unique. If you insist that it be completely local like this and diffeomorphism invariant, then this is really the only metric that you can construct. If you furthermore set C equal to 0 but force a relationship between A and B here, then you have a slightly simpler metric which was defined first by Ebbin, and that's been greatly studied in the pure math literature as a metric on metrics for a long time. Okay, so notice that we don't have the derivatives that Peter Meeker talked about on Monday here. That would damage this locality property. They may be interesting metrics, but it would certainly make computations more difficult. Okay. Okay, so this full elastic metric, I've talked about how it satisfies the first two of our desiderata, but unfortunately it doesn't satisfy the third, in the sense that despite its simplicity, it's still very difficult to use this metric efficiently. So you can do computations with it. They're extremely long, and I'll talk about that in a minute. However, there is a very nice subclass of this metric, which is the one that we'll actually use. So notice that this piece, so this is the first and the third terms in the metric, with the particular values for the parameters A equals C between them. And notice that if I call this R and I call this d theta squared, this is essentially just the Euclidean metric in spherical coordinates. And because of that, I can change the coordinates and define this quantity q, which is the radius quantity times the unit normal vector, and that is now Euclidean coordinates. And these Euclidean coordinates exist at each point on the embedded sphere S2, and if I calculate what the small change in q corresponds to, it generates, of course, exactly this, because this is Euclidean and this is spherical coordinates. And so I'm going to define this quantity q by this map here and call it the square root normal field. And this is exactly the analog, for those who know about it, of the square root velocity field in the case of curves. So if we set b equal to 0 and put a equal to c, we end up with exactly this metric here, which can now be rewritten in terms of q in this form here. And you can see now that it's dramatically simplified. This is simply the L2 metric. It's effectively Euclidean. It's flat. The space, this metric has zero curvature. And that's going to dramatically simplify everything that we want to do in terms of surfaces. That's not to say this is without issues, and I'll get to those issues in a minute. So this is the metric that I'll talk about from now on. So what's good about it first, before I tell you what's bad about it. So if we don't use this simplification of the metric, or in particular, even if we don't use this quantity q, then if we want to do statistical analysis using the elastic metric, it's very expensive. Okay, so the elastic metric is written in terms of metrics of normal fields. We have to rewrite it in terms of surfaces, and we have to evaluate everything in the surface space. And this is a very expensive thing to do. So, for example, to compute the distance between two surfaces takes around 2 hours. And if you imagine that to actually calculate the mean of a set of shapes, you have to do this many, many times, you begin to see that this is computationally not feasible. On the other hand, if we have this quantity SR and F and we restrict to this partial elastic metric, then we're essentially in the standard statistical scenario where we have RD, if you like. In theory, it's infinite dimensional, but essentially many things are the same. So in particular, for example, the shortest path between 2 points is simply a straight line. in this Q space. Again, there are questions about this I'll come back to. Distances are trivial to calculate. Rotations, the alignment between two surfaces is now in closed form. Because we know the geodesic, all we have to do is align one surface to the other, whereas if we don't know the geodesic in closed form, we have to align, calculate geodesic, iteratively, and it's very expensive. Scaling, which I haven't really mentioned but is important in many applications, is particularly easy to deal with because it turns out that unit area surfaces have unit norm in this metric. So unit area surfaces lie on the unit sphere in this L2 space. And calculating means, for example, is again trivial, essentially the same procedure as you would use in standard statistics. So this is great. Everything works beautifully. Everything is greatly simplified by using SRNFs, but there is a fly in the ointment, and that is that if we want to be able to use this, having calculated the average Q in the Q space, we need to be able to transform it back to actually get the surface. What is this average surface? And in the case of curves, that's a relatively trivial problem, just involves an integration. But in the case of surfaces, it's no longer a trivial problem at all, as you'll see in a minute. And in particular, it's not clear if this Q map, which is mapping you from surfaces to this L2 space of Q functions, SR and Fs, it's not clear that it's injective. So it may be that two surfaces map to the same values of Q. Globally, it's not clear that that's true, but even locally, it's not clear that you can't make changes in a surface that map it, that don't make any change in the Q function. And it's also not clear that it's surjective. That is, if we take some random Q function in this space, is there a surface that corresponds to it? Actually, the answer is almost certainly no. So we have to deal with that problem. So we have these questions. When does there exist a surface that corresponds to a given Q? If it exists, is it unique? Up to translations, because we're dealing with derivatives, so we'll never recover the position of the surface. Okay, so what do we know about these problems? So there's some past work which is related to this, so I'll just recap that quickly. I'm rapidly going to run out of time, I can see. So I gave this talk in Florida about a month ago. Some people have seen it, I think, when I ran overtime and I had half an hour, and I thought that this time it would be probably about the right length, but I think that won't be the case, as it turns out. So what is known? So it turns out that if you have the full metric of some surface and you have the unit normal field, excuse me, then it's known that the surface can be reconstructed uniquely up to a translation, but there are constraints, and they're somewhat complicated. They involve the curvature of the surface and the third fundamental form, but given those, and if you implement those constraints, in principle at least, you can reconstruct a unique surface. There's an interesting case where if instead of, so I'm talking about the case where we have R and n hat essentially, because given Q, perhaps I should make that clear, given Q, it's easy to reconstruct R and n hat separately. So that's the information that we have. Turns out that if instead of R you have this G hat, then again the surface can be reconstructed uniquely up to a translation and a scale. This is quite surprising. This is an overall scale, so this gives you in some sense the surface up to possible local scale transformations, but it turns out you can still reconstruct the whole thing up to a global scale. But again, this is even more complicated. In this case, there's a complicated third-order differential equation to put constraints on these things. So what about our case? Well, it turns out, so this was a depressing moment when I found this out, that V.I. Arnold, the famous mathematician studying classical mechanics, among other things, has a book of problems. And the first problem in this book is exactly the problem of can you reconstruct a surface from these two quantities. So given R, which is some sort of area measure, and a unit normal vector, when is there an immersion F that actually generates these? And clearly that question was not known at the time, and it turns out that 14 years later, another book was published where a bunch of people who had been mostly students of Arnold's commented on the problems that he'd laid down, but sadly there's no useful comment on this problem. So apparently this problem remains. I assume that if he couldn't solve it, probably is unsolved, and certainly my chances of solving it are negligible. So it's clearly a difficult thing. We do know some things, however, that we've sort of actually worked out for ourselves. So first of all, to be an immersion in the first place, this normal field has to be non-zero everywhere. by definition. The surface has to be closed, which means the integral of this n over S2 has to be 0. And finally, we want the degree of this mapping. So n hat is a mapping from S2 to S2, so it can wrap potentially multiple times around the target sphere, and we need that degree to be 1. This is kind of an interesting point in itself, actually, parenthetically, is that you might expect there would also be the case -1, but it turns out that all immersions of spheres have degree 1, and you can flip a sphere inside out in a smooth way. So this is a useful constraint to have. So the question is, are these enough? So if we have these, does that imply that the corresponding there is a corresponding surface mapping from S2 to R3? So that's the existence, and these are some constraints that actually we can apply reasonably simply. There's some questions also about uniqueness. So Peter Mekor had an exchange with Rob Bryant on Stack Exchange, actually, about whether this differential equation, so if I set this df cross df equal to some quantity, when is it solvable? I found the response hard to understand, but one thing I did garner from it is that it's only a local solution, and in addition it's not unique. So the global question of existence isn't really addressed, of uniqueness isn't really addressed by Rob Bryant, who wrote the answer to this. Eric Klassen has come up with an example for open surfaces in R3 where uniqueness is definitely violated. In other words, there are two surfaces that map to the same Q, but I think that's fixable because there are no boundary conditions in that case on the parameterization on the surfaces, and they should constrain the parameterization in such a way that it should be fixable in the same way that you need boundary conditions to solve this PDE. But in particular also for sphere immersions, we don't know anything. So what to do at this point is the question. And so I'll talk about now about work that we've done to try and essentially hack in a reasonably logical and sensible way the fact that we don't really know anything about these maps and don't know how to invert them. And what we do is we essentially try to we rephrase the inversion problem as an optimization problem. So if there is a surface that corresponds to a given Q, then when we map F via Q into the Q space, it will coincide with a given Q, and the distance between them will be 0. So what we're going to actually do is, for a given Q, look for a surface that is as close as possible to whose Q function is as close as possible to the Q that we actually have. So we search over the space of surfaces. For each surface, we map it into Q space, and we calculate its distance, and we try and shrink that distance as close to 0 as possible. In practice, what we also do is we align the surfaces as we go along. That's not strictly speaking necessary because we're searching over all surfaces, parameterized surfaces, but it speeds things up a fair amount. So if we can solve this problem, we get several benefits. We get some sense of consistency. So we don't know, of course, that there may be more than one minimum, more than one minimizer for this problem, and there certainly may be local minima. But because we're solving the problem we will solve it in essentially a local way, we will kind of get consistency between local Qs. So if we find a surface that corresponds to a given Q, and we look at a next door Q, we're going to find a function that is close to the first function, probably. It's useful in that it also works sensibly even if there is no surface. So whatever we do, we'll find some kind of surface that is close to the Q. Okay, so in that sense, it's very useful because it sort of finesses completely this question of existence of the surface. So we initially tried to do this using gradient descent. It's very naive gradient descent on this energy. It's very slow and it's very wrong. So this is a spiky, synthetically created, as you can tell, a spiky surface. We initialize gradient descent with a sphere. We try to reconstruct this surface from its Q function, and we get this mangled, sort of bizarre, completely, the numerics are completely wrong. It's very difficult to actually deal with it. So to get around that, we used a multi-scale type of approach. So this is a very common type of approach, both to speed things up and to avoid local minima and make things better behaved. We did that using a spherical wavelet decomposition. So what do I mean by that? So we can create from a fine scale surface, we can create a sequence of coarser surfaces, and we do that by calculating spherical wavelets on the surface. It means we have to convolve some filter with the surface, which we do using spherical harmonics, and generate a series of coarser and coarser representations of the surface. if we had these, from these we could calculate the corresponding Q functions. So this thing here is a multi-resolution Q function by definition. And if we have this, then we can use it to try and reconstruct this surface in the following way. Again, we start with a sphere, but now we simply try and reconstruct the coarse resolution surface. Having done that, we use that as the initialization to try and add extra detail and so on and so forth. So essentially we're adding, you can think of it as adding subbands of the wavelet decomposition as we work our way through this sequence. And this works very well, empirically speaking. So we get very good reconstructions. So here are some...
You need to have the series of low resolution Q version of the...
Right, so yes, you're absolutely right. And I will get to that in a minute. So we're not constructing, you'll see in a minute that we're not, what you want the Qs to correspond to different resolution surfaces, so it's not really very obvious what you should do to the Qs to actually generate that starting from a high resolution Q, but in fact we never need to do that, as you'll see in a minute.
You start really from a parametrization, or is there, so you do some conformal mapping to the sphere, or you have
to get an initial parametrization of the surface? Yeah, so well, I mean, assuming you're just given a mesh as opposed to some parametrization in the first place, which is typically the case. So Hamid Laga, who I mentioned at the beginning, he's an expert on putting spherical parametrizations on surfaces. I don't think it's conformal, actually. To be honest, I'm not exactly sure what he does, but its critical properties, it's very fast to do this, and it gives very, very smooth, nice spherical parametrizations of the surfaces. So we usually end up with a nice starting parameterization. But you're right, that's in the background if you have mesh data, certainly. So these are a set of target surfaces. These are our reconstructed surfaces, and these are the errors. You can't see anything here. This is scale of pixel-wise errors, so it's the distance, local distance between the original surface and the reconstructed surface. And these errors are all much less than 1 pixel, right? So we're 1 voxel rather. So we're reconstructing the surfaces to a very high accuracy, even in the case of these surfaces with very thin pieces.
In your bad example, did you get the correct Q, or did you get the same distance? I mean, when you were doing gradient descent to start with, what kind of minimized error did you get?
Actually, I don't know, but I really think that numerics just didn't work very well. I think it was, I mean, perhaps we could make that work if we did it for a very long time with an enormously small time step and a very high resolution representation of the surface. But no, I don't know what the final, this is a good question, yeah, you mean what the final distance was that we actually got. It must have reached the termination condition of the algorithm, but how meaningful that is, I'm not really sure. So this is just another example, so I have, I guess, a few more minutes. This is an example of reconstruction of surfaces from the Shrek 07 database, which is a whole bunch of, actually a subset of it, because we're dealing with watertight surfaces, so-called, which means they're essentially embeddings of a sphere. And these are average reconstruction errors, box plots, which again are rather small probably from where you're sitting, but 0.02 is this number, and that's 0.02 of a pixel again, so these reconstruction errors across this database are very small. The time taken to do this depends on how we do it. So if we use spherical harmonics to represent the surfaces, it takes about 15 minutes to do a 64 by 64 mesh grid. However, we can also use PCA, which I'll talk about in a minute, to construct bases which are specific to the data set. And in that case, we can use far fewer basis elements, and computations are down to the order of a minute or less to do these reconstructions. Okay, so this relates to Alain's question. So I've just talked about reconstruction. How do we use this to actually calculate geodesics and distances, or geodesics in particular, between surfaces, distances we can do easily. So I was very proud of this diagram. It took me hours to make this, but it's it's actually not very clear at all, I realized looking at it this morning. So the goal is to compute a geodesic between 2 functions, so f0 and f1 here. And how are we going to do that? The first thing we do is we construct multi-resolution representations of those surfaces. Okay? Given those multi-resolution representations of the surfaces, we can then construct what is completely buried here, which are the multi-resolution Q function versions. So that's how we get the initial Q functions. And having done that, we can then essentially draw straight lines between the different multi-resolution points here, and these are the geodesics in Q space between these endpoints, multi-resolution endpoints. And then for each point on the geodesic here, we have a multi-resolution Q, and we can reconstruct it in the same way that I described a couple of slides ago. That's one way to do it, and the advantage of that way of doing it is that we can calculate any point on a geodesic wherever we want without reference to the starting or end points of the geodesic. Another way to do it would be to use a kind of initialization moving along the geodesic, which also is useful for some purposes and maybe slightly more effective sometimes because you have a slightly better initialization. So we, as I just said, we compute the multi-resolution Fs, we compute the multi-resolution Qs corresponding, we compute the straight lines between the multi-resolution Qs, and then we minimize the matching function to get back the multi-resolution and eventually the fine resolution surface. And this is an order of magnitude faster, at least, than doing it in the original surface space. So you, like I said, it took 2 hours there, and it's very much quicker here. And in particular, for finding mean surfaces, it speeds things up enormously, where you need many, many geodesic computations. And it also leads to nicer results, so I'll flip over this quickly, but the behavior of surfaces when you calculate geodesics in the Q space, because it has such a nice geometric interpretation, I think is the root cause of it, have much nicer, in some sense, more physical, for no necessary reason except that it's geometric, than they do if you calculate using a simple metric in the surface space. What tends to happen in the surface space is that you get shrinkage of shapes, very peculiar behaviors, whereas in the Q space you get very natural deformations, even of something as complicated as a human body. Now remember, I'm not claiming particularly that we're going to use this to construct, to interpolate computer graphic sequence in the next, in the next Pixar movie. It almost certainly isn't accurate enough to do that. But what this is telling you is that there's something natural about this metric which will make it easier to build on top of it statistical models that make them simpler essentially to build. So here's just some more examples showing how we can get these really large-scale deformations across between different body shapes, different poses, and so on and so forth. So I'll just take a couple more minutes. I was going to go into some depth about this, but I won't do that now because several other people have mentioned it. So how do we construct statistical models when, in a way, the most simple statistical model that we can construct is a Gaussian distribution? There are many ways to define that. We heard one using diffusion earlier on in the week. There's another way using maximum entropy. We can also do what's known as a tangent space Gaussian. And here what we do, just to cut a long story short, is given a whole bunch of samples of shapes, we calculate their mean shape, which is the shape which minimizes the squared distance to all the others. And at that point, we put a tangent space on here, and we now calculate a covariance in that tangent space using points which are lifted from the space of Q functions up into the tangent space here. And we're in a flat space, we can calculate a covariance, we can put a Gaussian distribution on here, and now in principle, although in practice one never does this, you can push this back down, wrap it back down onto the Q space to get some well-defined distribution. This is a useful thing to do because it's very easy to sample points from such a distribution. You simply have to sample from a Gaussian distribution on the tangent space and then project it down to get a Q function and hence a surface. Parameter estimation I already described, it's very easy. And also we can easily perform PCA, and this has been mentioned a couple of times, up in the tangent space and reduce the dimension of our model. It does have disadvantages. You can see already that, for example, if I was on something as simple as a two-sphere, I'd have to truncate it because the Gaussian distribution will wrap around many times. But also it turns out the density on the sphere has some very peculiar properties because there's a Jacobian of this mapping. Because of the curvature, you tend to get density build up around the lower parts of the sphere. And so actually the density on the sphere with respect to the standard metric has a sort of pickup towards the South Pole. But provided you keep the variance low, that's not a big problem. Okay, so using that, you can, I'll describe this slide and then flip on to the last slide and then conclude. So using that, you can construct, for example, models of human body shape. So here we construct, we have a bunch of human body shapes. We have neutral poses, which are like this. We construct a model of shape based on the neutral poses, and we construct a model of pose based on bringing all those poses, excuse me, back to the mean. Excuse me. back to the mean neutral shape, and then building a Gaussian model of those as well. And then we can sample new human body shapes by sampling a new shape of the neutral pose, and then a new pose for that neutral pose, and then parallel transporting that pose onto our new shape. And these are just some examples of, again, very sensible looking human body shapes that arise from these, what are essentially quite trivial models. Okay, there's some stuff about classification and clustering. I think what I just want to do very quickly is to show these final slides on multidimensional scaling. So here, the different colors correspond to different classes of shapes from the Schreck database. And multidimensional scaling, I'm sure most people know about it. We simply try and project them from their very high dimensional space into R2 in such a way that the distances are preserved as well as possible. This is what happens if you simply use a Euclidean distance between surfaces without them being registered, and naturally enough, you get a mess. But if you register them and still use the Euclidean L2 distance between the surfaces, you still get kind of a mess. Some classes are beginning to separate, but it's still very confused. But remarkably, and it's very surprising. I don't understand really the reason why this happens, but nevertheless it's indicative of why the SRNF is a very useful thing. If you do this in Q space, then suddenly these shapes get much better separated than they were before. There's still a couple of classes here which are mixed together, but you can see that this kind of separation between surfaces will dramatically simplify classification and potentially many other problems.
But don't you register them in Q space?
Right, so registering the registration for the L2 in surface space was done actually in Q space because it's just so much faster. Yeah. Sorry?
That's maybe why it clusters better in Q space.
I wasn't clear. This registration is also done in Q space, and then
but if you use, the cluster for the Q distance, the distance in Q space are going to be smaller because this is where you did the registration.
Yes, I guess that's true. Yeah, maybe. Yeah, true.
The red and pink ones are actually better on the left. The red triangle.
The red triangle. Yes, that's true. They are. Yeah, absolutely.
So maybe the next dimension will separate those.
Yeah. Yes, possibly. Yeah, absolutely. Yeah. This is a trivialized representation of the distances. So.
Probably does.
Okay, so just to summarize, so this SRNF gives you very efficient registration, even under quite large deformations, and it Euclideanizes this Riemannian metric that we can use to perform all the analyses that we need. And as a result, statistical analysis of surfaces becomes relatively straightforward in the same way that for curves the SRBF simplifies things. So we can do all the usual things with surfaces in a way that is more tractable certainly than it was before. One thing that I'd like to mention, I won't have time to describe it, is that we can also put landmarks on these surfaces and then constrain the deformations to match these landmarks, which is an interesting, for many applications, that's a useful thing to be able to do. However, there are many open questions, which I've mentioned most of. For the full metric, can we actually use it? Can we use the constraints? Can we invert it? We know it's invertible. Can we find special cases that somehow simplify the computations? And then for the partial metric, there are all these technical questions about whether the closure and the degree being 1 are enough to specify the image of the surface space, whether it's injective. And then there's another question about whether we really care about immersion. So in the case of curves, we tend to talk about absolutely continuous curves. So there's a question about what the appropriate space is in the case of surfaces. It's not completely obvious because now the normal vector, rather than being linear in the surface, is quadratic in the surface. So it's not really clear what this, to me anyway, what this space should be. So these are all interesting mathematical and practical questions that we'd like to address. Thank you very much.
So given what you said, what we don't know about properties of the map Q, how do you know that you're actually computing geodesics between surfaces using your inversion method?
So you don't, actually. In fact, you don't know that you're computing them. This is not quantified at all, right? So we just hope that to some extent they will be approximately close to geodesics. And they tend to be, because we can calculate geodesics back in the surface space using the same metric, right? So Sebastian Kurtek has done some work on that, where you pull back the metric to the surface space, and then it's very laborious, but you can calculate geodesics. We haven't studied in detail the match between the two, but they're not hugely different from one another. certainly. So the distances that we get, and that's Laurent's question again, I'm afraid I don't offhand know the answer, is when we do this inversion by optimization, how small are the distances that we get? Pretty small, because the surfaces, reconstructed surfaces, are very close to the original surfaces. So we haven't, to my knowledge, we haven't found a case where there simply is a huge remaining distance between the
question. I mean, to be trying to reconstruct the midpoint of the geodesic, because for that you don't a priori know whether it really corresponds to a surface or not.
No, so what we affect, exactly so. I mean, as I said, what we're doing is calculating a surface which is as close as possible to that midpoint. No, that's absolutely right. I mean, we would then need to impose the constraints, which we actually is the next thing to do, because we have an idea of what these constraints are, at least a subset of constraints, to impose those to try and find geodesics that only lie in the constraint space and study how different it is. But remember, the surface reconstructions are generally very good in terms of matching things. So that is an indication that the surfaces work out.
Just a comment. I'm very impressed, and I think this is a very good work. And it poses lots of questions for mathematics proper.
Yes, not me, I think, but yeah. Thank you very much.
I agree, and that's
Thanks.
good that you keep Peter busy for.
Yes, exactly. I hoped he would just come up with the answer.
So you mentioned the computation 2.5 minutes for the Shrek database. Is that 2.5 minutes for the whole lot?
No.
No, take one.
No. 2.5 minutes to invert. Wait, which one was it? So 2.5 minutes was to invert a 128 by 128 mesh function from its Q function. Yeah, I mean it definitely room for improvement, and I mean, so it's quite possible that there are ways of speeding that up that we haven't. I mean, PCA is one way of kind of sparsifying it in some way, but there may be other effective ways of doing that. That's right. Yeah. I forget. I think there's something of the order of 15 classes or something like that, with a similar number of shapes per class. To invert them all, yes. Yeah.
But it would be impossible with the...
It'll be complete. Well, you have to be very patient.
Yeah.
How you deal, maybe I missed something, how you deal with the reparametrization of the sphere? There is no fun.
At which point, for the optimization, for the
Yeah,
reconstruction?
when you have your two shapes.
What was the question?
So there's two situations. One is registering the shapes in the Q space.
Yeah.
So that's a search over diffeomorphism. So that's done by a kind of gradient descent procedure. So there's no guarantees that's actually finding the optimal. So it's the same thing
Yeah,
that's
because
done
for the curve you have this
it's the
dynamic
same.
programming.
Yeah, you don't have that, right?
So here what you're doing something.
We're doing some kind of initialization and gradient descent on the diffeomorphism, but it's as far as I remember anyway. I think so, possibly with multiple starting points. But that's not what we're doing for the reconstruction. That's slightly different. So for the reconstruction,
Yeah, but when you want to compute the distance between two shapes, you need to do that.
so again, talking about whether it depends whether you're talking about the reconstruction, which is aiming to reconstruct a parametrized surface, a specific parametrized surface, or you're talking about simply calculating a geodesic distance between two Q functions. So in the latter case, it's a gradient descent type of procedure on diffeomorphisms.
Yeah, because when you want to compute, okay, it's just in the quotient space, so you want to compute the distance of the
Yes, exactly so. No, so that's
surface up to reparametrization.
so that's. I mean, it's this in principle, it's the same as in the curve case. It's just that in the curve case, you have this nice dynamic programming type
so
of method.
in this case, you need to do.
So in this case, we're using a sort of a local optimization, essentially.
Okay. So when you compute all this, when you did this, compute all the pairwise distance between the shape of the Shrek database, you are doing this.
To calculate that, yes, absolutely. They're fully registered, so they're registered over reparameterizations, but also over rotations. Not scales, I'm not sure, I can't remember. I mean, so in the sphere, I mean, we can also, like, perhaps I should say that, I mean, unit area, because unit area surfaces lie on a sphere, it's easy to calculate geodesics of all of which lie in unit area as well. So, but for the reconstruction, we do a different thing. We don't need to search over parameterizations, but actually we do a kind of global coordinate rotation on the domain sphere just to speed things up.
So let's let that be the last question in the interest of lunch.
Yeah.
So, thank you.
Thank you.